On behalf of Partners of Project Green, I would like to welcome you to our monthly series of green technology webinars. For those of you who might not know, Partners of Project Green was developed in partnership with Toronto Region Conservation and the Greater Toronto Airports Authority, and is a growing community of businesses working together to green their bottom line by creating an internationally recognized eco-business zone around Toronto Pearson. Before we start the webinar, I would like to run through a few logistical items. To avoid static feedback during the recording of this webinar, please turn off all audio on your laptop. Also note that your lines have been muted to avoid background noise. Questions will be answered at the very end of both presentations via the chat section located to the bottom right-hand corner of your screen. You're more than welcome to type your question in the chat section throughout the presentation so they are not forgotten during the Q&A session. But as I just mentioned, they will not be answered until the very end. If you come across any issues throughout the webinar, please send me a direct message by clicking on my name to start a chat. So let's begin. This month's Green Technology webinar is focused on air compressors. We are very fortunate to have Herb Sunnock from Sheridan College and Klaas Bakkesten from Golder Associates joining us this afternoon to give us an overview of a proper system design, identifying inefficiencies, and providing examples of companies who have improved their systems and as a result reduced their cost. So first up is Herb Sunnock. Herb is a manager of Applied Research and Sustainability for the Faculty of Applied Science and Technology at Sheridan College. As a certified energy manager, he spends a lot of his time at local manufacturing and commercial facilities assessing and identifying opportunities for energy and production efficiency. Now you could take it on, Herb.
Thank you very much. Well, good afternoon, everyone. It's my pleasure to be with you to discuss opportunities for saving energy and money on your compressed air systems. Klaas and I have arranged our presentation so that we'll start in the plant on the supply side and we'll move back steadily towards the compressor room. That follows the logical progression that's going to yield the biggest savings for you, namely defining the needs for compressed air that you have, examining your system design in support of that, looking at very carefully at whether all the components are working, and then you get to your compressor selection, sizing, control, and those aspects, versus starting at the compressor room and then guessing what sort of needs you have. Now, whether you're the boss or you've convinced the boss to let you attend the webinar, I really want to make sure you come away with some key messages and key takeaways that you can bring back and work with either the speaker next or coming into the future. And in general, what we need to get at today is just how expensive compressed air, where do we find opportunities to use less compressed air, how do we improve the system, and how do we maintain at peak efficiency. The first takeaway is that compressed air is very, very expensive. You can see right away 91% of the energy you put into your compressed air system is lost before it does any practical work for you. And the bulk of that, as you see in the blue section, is just heat that arises from compressing air down. As you compress air, it heats. And that heat is released primarily into the atmosphere through your receiver, through your piping, through aftercoolers, intercoolers, and all of that. And then you've got sort of cumulative losses on top of that from systems like your dryers, your filters, leaks, and some conversion. In fact, sorry, just continuing the thought on that slide, if you were paying 7.5 cents per kilowatt hour for electricity to run your compressor, at 9% efficiency, that means you're getting kilowatt hour of air power for about 83 cents. If you blend in the cost for electricity demand, which gets you to about 12 cents a kilowatt hour, that's probably like $1.40 per kilowatt hour of air energy that you're using in your plant. And the way you can sort of compare that is think about using a pneumatic tool versus an electric tool. And what you'll find is the pneumatic tool is costing you about 15 times what it costs to operate the electric tool. And the consideration there is if you've got somebody who's doing an 8-hour shift and working with, say, like a pneumatic grinder, that pneumatic tool is going to be much lighter than the electric tool, but at a cost. And you need to be cognizant of the fact that you're making that exchange. Now, before I start talking about end uses and opportunities at end use to think about saving compressed air, there's two barriers that we should sort of keep in mind, two caveats. The first is that process is pretty personal, right? This is your baby. This is your production. And at the talk earlier in the week, the speaker was talking about innovation of product and process. And he said you have to have kind of an out-of-body experience, float up over your product and imagine its use and look very critically at it. And the same is true with this kind of end-use stuff. You really have to look broadly and objectively, if you can, to achieve the kind of savings you want to get. The second thing is that your process is probably working and you're really afraid to break it. You really don't want to be in there tinkering with it when it's affecting your production. So just with those two things in mind, this is the context in which I'm presenting some possibilities for saving at end use. And the first is to look where you might be using what we call open blowing. So basically you've got a hose attached to your compressed air system, you've got high flow rate going. And those kinds of uses might be cooling something like a bearing, or drying or cleanup, draining compressed air lines, clearing conveyor jams, things like that. But you have technology like nozzles that could reduce the CFM at that end use by about 50%. And you can put a regulator on that and make sure that you're not putting higher pressure air through that than you need to. Sparging is another one. So now you're aerating, agitating, percolating some kind of fluid with the compressed air. Now, if you're dealing with an explosive substance, you're probably using the right technology if you're aerating it with compressed air because you don't want sparks. But if you're not, the real issue with this process, in addition to using a lot of compressed air, is your little compressed air bubble that enters the fluid begins wicking your product, the product you're mixing into the bubble. The bubble reaches the surface and it releases your product. So you're actually losing a bit of product through that kind of mixing. So an alternative there would be mechanical or electrical mixing. The next series of applications are areas where you could probably use a blower. So aspirating is entraining the flow of another gas using compressed air. So you might use a blower to get the stream of gas going. If you're atomizing a mixture, you might use a blower instead. If you're offloading, say, cargo containers, and you're currently using compressed air to try to force the solid or liquid out into the plant, then again, an application for maybe a lower medium blower. Transporting solids, pneumatic conveyance is another one where if your primary thing is really getting a good flow, you may just need a good blower. And vacuum generation is one of those where if you're using it less than, say, 30% of the time, it looks like the economics play out that you're okay to use compressed air to do vacuum. But if you are using more and more of that, maybe like close to 100% of the time, then consider doing a vacuum pump. The economics will work in your favor. And then there are some things like cooling people and cooling cabinets that should just be a fan. Why would you spend the money? Why would you spend $1.40 to cool somebody else? I think you could do it with a fan. And then the unregulated end uses. So the idea here is just, rather than having the open blowing and a hose, put a regulator on it, make sure you're controlling where that air ends up. And a lot of times in plants, we see that there's been a reconfiguration of equipment, that things have been moved around, or that some line of compressed air has been extended for future expansion. And yet that line is live, and if it has any leaks on it, it's basically wasting air. So those should be either capped or put a valve on it, something to keep air from flowing down that and potentially feeding leaks. In this chart, I'm just trying to highlight what it actually costs you to feed leaks. The nasty part of an air leak is it's not messy like water, steam, or hydraulic oil leaks. You see those, you see a puddle, you go and fix them. And the air leak you may not pick up on. And so it's easily ignored what that costs to you. Just as a note on this to help you kind of follow, the leak diameter on the left gives you an indication of the size of the opening. And it's not a hole, per se. It's probably more like leakage around a coupling or something like that. And the corresponding flow rate is in the next column. And then costs, annual costs, based on the kind of shift you run. So if you're running, say, 1 8-hour shift, Monday to Friday, you'd be in the left-hand column versus the 24/7, 365 in the right-hand column. But a note on that as well is if you happen to be leaving your compressor on through nights and weekends, you're over in the 24/7, 365 regardless of when you're operating. You can see right away that a 3/8-inch leak would have a very substantial cost to you each year. And one other thing, just to give you context here, is that 8 to 10 CFM would be a leak you could hear. So that leak's costing you something like $500 to $1,000, let's say. And the little sort of nasty little piece of this is that those leaks you can't hear, the ones that are below 1/16 of an inch, we find a lot of those when we'll go around in the plant with an ultrasonic leak detector. You probably have maybe a dozen or more of those, maybe quite a few. And you could see that on a 3-shift operation at $200 a piece. Those cost you very quickly. To give you a little more perspective on the CFMs, we tried a little graphic here using a tank of 250 cubic feet, which is essentially like a 10-foot high tank with about a 5.5-foot diameter. It's fairly big, a standard size, but a big receiver tank. And we wanted to convey to you how much of that tank's capacity would be used feeding leaks of various sizes. So a 1/64-inch leak is using only about 1/10 of that, but as you get up towards a 1/8-inch tank size, 1/8-inch size leak, it's about 6 tanks per hour. And as you get even bigger on leaks, or you go towards open blowing at 3/8 of an inch, you can quickly see that so much of that capacity is being fed to the leak. This is not something we want. So, if I've convinced you that we want to be looking at leaks, where are we going to find them? Well, here are some of the usual suspects: couplings, fittings, pipe joints, any spot where I've got a junction, where I've put some pipe thread, the pipe thread and I've wrapped it in Teflon tape. Hopefully I've put some Loctite or something on there to actually really seal that. But often we find those 1/32-inch and 1/64-inch kind of leaks around those kinds of things. Also hoses. More often than not, we find hoses in plants that have hose clamps. They have the standard garden hose clamp. That almost always leaks. So if I'm walking through, I would find maybe 75% of the hose clamps are leaking in some way. The preferred alternative with compressed air is a crimp-on connector. So it's worth the extra investment to get that connection right. And also what we see are those plastic hoses like you see leading to the air blow-off gun. Or sometimes we see them fed to a regulator assembly on the back of a CNC machine, something like that. And those things, if they're fairly lightweight, they end up splitting, and you get a good hiss out of those. Right? So it's worth their investment in a bit of a heavier duty hose, but also paying attention to the fact that those are going to begin to wear. Another common spot, speaking of hoses, is the hose reels like you see in the bottom center. Virtually every one of those I come to has a leak in it somewhere, and I think the most common culprit is when you've got the source of air that runs into the hub. And that seems to be the spot that's leaking, so something to pay attention to there. But other little spots where you might find a bit are around your filter, regulator, lubricator assemblies, because you've got so many seals and connections. In quick connects where the seal is deteriorated over time, you might get some hissing on those. We find condensate traps where they've been cracked open to let water drain out, but all the water's gone and now it's just venting air. And then another one that's kind of surprising, which is the little solenoid-operated drains at the bottom of receiver tanks. I was in a plant last week that was wonderfully managed. It looked like they were really paying attention to the compressed air system. It had a few issues, but we walked into the compressor room and straight away you could hear hissing. I walked right over to the receiver tank, and sure enough, the drain solenoid was wide open, stuck open, and we were bleeding air off the system. It happens. You got to pay attention to it. The next little piece, once you've sort of satisfied that perhaps you've handled some leaks, you've looked at some of the end uses, are these little niggling pressure drops. They just come at every component of your system. So it could be around a filter that's a bit clogged, can be in hoses that are too restrictive, it can be in components that have some corrosion. You will find pressure drops wherever there is some kind of obstruction, resistance, roughness, or leaking. So at the end use on the hoses, the filter regulator, lubricator, and the hoses at the end, you'll find a significant amount of pressure drop. It should only be about 7 psi. Air oil separators, after coolers, moisture separators, dryers, those system components, if they're not sized correctly, can lead to excessive pressure drop. They also can accumulate moisture. They can also, therefore become a bit corroded, so add some pressure drop in the process. System piping, with a lot of 90-degree bends, restrictions, so you went from a 2-inch to a 1-inch, and then in the drop leg, those add up and will pressure drops. And the note on that is to pay attention to the configuration of your system. If you have one straight line through the plant, the end use is probably going to have, the very end of the line is going to have a more significant pressure drop than what's going on at the beginning, particularly if you have a high compressed air consuming process somewhere near the beginning of the line. A ring system there would provide a shorter pathway for air and minimize the pressure drop. Some rules of thumb to kind of keep in mind there, courtesy of class, would be a 2 to 3 pressure drop from 2 to 3 psi pressure drop from your master regulator to your end-use regulator. More than that would probably indicate that something in your system piping or the systems immediately following your compressor are causing excessive pressure drop. Now, one of the nasty bits about the pressure drops is that cumulatively, they rob your end uses of the power they need to perform effectively. And what ends up happening more often than not is the master regulator pressure is turned up. So now we've increased the amount of pressure in the system to try to compensate for pressure drops that could have been handled in other ways. So your system does have to account for the fact that you've got losses in your dryers, filters, piping, separators. But if your pressure is too high, not only are you consuming more energy putting compressed air into the tank at that high pressure, but you're also feeding your leaks at a much higher rate. If I can kind of get you to reflect back on that leaks table, the 3/8-inch leak was at 100 pounds was a flow rate of about 230 CFM. If that was reduced to 80 psi, that same leak is at 111 CFM, about half. So pressure has a quite significant impact on how much compressed air you lose through leaks, as well as how much energy your system's using. The rule of thumb to apply there is that a 2-pound increase in pressure is going to increase the energy requirement of the system by 1%. If you happen to be feeding unregulated air, open-blowing leaks, you might get another 0.5 to 1% increase in energy use for every 2 pounds increase in pressure. So it's a sensitive variable and something that you can work to reduce to save energy and money. Dryers are an interesting piece of the equation as well, because what we find is that in some cases, dryers are not working as intended. We went into a facility that we didn't connect the dots right away. They had a drain that was running too long on the receiver tank, and then I noticed the refrigerated dryer wasn't working. As we talked to the plant manager after our walk around, he mentioned that at some point a few weeks previous, the receiver tank had filled half full with water. And we put the dots together. Of course, the refrigerated air dryer not functioning properly. Instead of identifying that the refrigerated dryer was the issue for excess moisture in the system, they opened the drains more, so they actually countered with using more energy. But another consideration in this is picking the right dryer in the first place. A refrigerator dryer is going to get you a 35 to 39 degree Fahrenheit dew point. And the idea of that is to avoid situations where water is condensing out of the air in your plant. A twin dryer, twin tower desiccant dryer, like you see on the right, is a minus 40 degree F dew point. And really it's about pharmaceutical grade stuff. It's about when you need very, very dry air for your process, for your application. Even things like painting could be handled with refrigerator dryer, moisture, air water separators, good filters with fine particulate filtering, and remove all that entrained moisture and all that. You don't necessarily need a desiccant dryer to do it. The desiccant dryer, the issue with it is that you've got about a 15% energy penalty for using it. Another point I'd just like to raise, we're getting sort of near the end of things that I'd like to present on the supply side, but there's a couple of last bits to pay attention to. One is that sometimes compressors are sized looking at a peak load requirement. If you happen to have a load that's intermittent, it operates maybe 5 minutes out of an hour, you don't need a compressor necessarily that's sized to hit that peak. What you could do, and I've sort of graphically shown this in a very crude and it's very crude format, let's just say. I wouldn't call it scientifically rigorous, but the point of the graph is to show the idea and the concept of spreading out the CFM requirement. If you use a receiver, you use a locally placed receiver, or you think about the master air receiver, having enough capacity to feed the instantaneous surge while basically accepting a lower average airflow hit. And with that, you can keep the compressor size down. And the final points I would like to make are that maintenance is really critical to this peak performance. And this includes, I'm sorry, it looks like I've lost a connection to the network. So covering maintenance items, the key ones would be maintaining the lubricant level, so inspecting that on a daily basis, draining the receiver and the drop legs and traps so that you avoid water buildup, visually inspecting your system, looking for leaks, looking for noise and vibration, safety covers that are off, belts that look wrong. And really probably key is turn off and disconnect your power at the end of the day so that you're not running that 24/7, 365 kind of schedule. Then on a periodic maintenance basis, be sure to take a look at those pressure relief valves. Make sure they're actually functioning so that when you need them, they'll all function. Clean the cooling surfaces on your intercooler or aftercooler compressor. Look for leaks on your compressor. Check your system for leaks periodically. So we've seen the cost of that. Inspect and change lubricant. Look at your air intake filters and check your V-belts for tightening. And then finally, I don't know if you're able to see the slide or not, but a routine system evaluation will give you a chance to identify and perhaps catch problems early. So one thing you can do once you've gone through, you've leak checked your system, and you're fairly certain your end uses are good, you've looked around for pressure drops, you might want to put an ammeter on the input line to that compressor and take a look at how much electricity it's consuming. You might want to, sometime when the plant is actually offline, you may want to fill the compressor to full charge, turn it off, and see how long it takes the tank to depressurize to maybe 75% of its value. And note these things down. Look at the operating temperature. Use some flow meters. All of these things give you a sense of what you would expect the system to do. And if you repeatedly come back and check, and you see a poem in any of those values, it could indicate for you that somewhere along the way, you've got something to address. And with that, I'd just like to thank you for your attention. I look forward to your questions at the end of Klaus's presentation. And I will pass the presentation over to Klaus so he can continue on what happens when you're inside the compressor room.
Perfect. Thank you so much, Herb. Just so as Herb mentioned, please note that questions will be taken at the very end of the presentation. I know, Herb, that you are unable to, you're not logged on anymore, but Adeline Liu has given you an applause, and so has Dejan Skorik. So it was a great presentation. Thank you again. So just before we go to the next presentation, it seems our system has kind of frozen a bit. I've tried to add some points in the chat section, but I'm not sure if you're able to view them. So let's just begin. So Klaas is the Energy Management Services Leader at Golder Associates. He has managed several industrial utility projects from initial study, detailed design, and construction up to and including commissioning of energy projects. This work includes several feasibility studies and energy audits in the processing and manufacturing industries with a particular focus on energy and water efficiency over the past 25 years. So you could take it on, Klaus. I'm just going to try to get your presentation on. It seems to have frozen a bit. So if you can start, and I will try to get your presentation on. Klaus, and then if you could just press *7 to unmute your line. So we're not able to hear you, Klaus. If you could just press *7, that would be great.
Okay, I'm muted, I guess.
There you go. We can hear you now. I thought you maybe disappeared for a while.
Okay, no problem.
So we're just a little bit delayed on, it is frozen, so I'll try to get your presentation on, but if you could just move on without it, that would be great. So,
yeah, maybe first a quick overview of the compressor plant. So now after Herb's presentation out in the plant and what compressor is used for, once you have a good understanding of that, we walk into the compressor plant, and typically most industrial facilities that we have seen, as an average number, your overall electrical bill, typically about 10-15% is used for compressed air. So it's a sizable energy consumption. Some plants larger, of course. And the key equipment that we're seeing inside a compressor plant would be the compressors, of course, the cooling of the compressors, filtration, waste heat recovery, if that is being implemented in the plant, dryers, be it after-coolers, refrigerated dryers, or desiccant dryers that Herb spoke of, and of course receivers and filters. Looking at different compressor technologies, compressors are typically in two categories, positive displacement, which are the most common ones, and dynamic compressors. Positive displacement used to be a number of reciprocating compressors, either single or double acting compressors. These are oil lubricated compressors. Currently, and since the 60s, more and more rotary screw compressors have been installed and tend to be the dominating compressor used. And these are of a helical screw design. There are also some rotary compressors using a sliding vane or a rotary blow. And the rotary compressors can be lubricated or oil-free. Dynamic compressors used for heavier and larger loads are typical centrifugals and are oil-free just simply because of the nature of the compression. Okay, great. So I'm just going to move forward on the slides here. And as I'm focusing the presentation more on the screw compressor, which is the most common compressors in mid-size facilities, there are two typical designs of screw compressors, either oil-free or flooded oil-based compressors. And the oil-flooded design, basically, the oil provides a seal between the rotor and the cylinder. So basically, lubrication absorbs the heat that Herb spoke of. The compression ratio to reach 100 psig is about 8 to 1, and a single stage would bring you to the pressure that is required by the plant. Typically, the discharge temperature is about 100 degree F and above the ambient. So in a compressor room, which might be 80 degree Fahrenheit, you might be dealing with about 180 degree F temperature on the compressed air. The non-lubricated style design of screw compressors, the rotors are machined much closer, much closer tolerances, and are operating also at a greater speed. But the compression ratios that you can reach with a non-lubricated design is lower, so it's typically 3.5 to 1. So a typical screw compressor delivering 100 psig would have 2 stages of compression, so 2 set of screws to reach the typical air pressure of 100 psig. By looking at the compressor sizing and how we typically size the compressor plant, just a comment, typically most air compressors are operating very efficiently at max load or at full load. At part loads, no compressor is working very efficiently. So you strive to design a plant with control system that has a system maximizing the number of compressors running at full load and minimizing any machine running at part load. And for smaller size plants, you would typically add, say, a 3rd compressor. If we're looking at sizing a plant for 2 compressors, as the following slide would show, you might have a 3rd one as for redundancy to allow for breakdowns and things of that sort, allowing you to continue producing with the 2 compressors and the 3rd one in maintenance mode. On larger systems, rule of thumb tend to be on water-cooled systems 30% over design in the size of the compressor, in the capacity, so that you can handle some extreme peaks or some maintenance shutdown of one of the compressors. Looking at the 2 compressor technologies and the type of controls that you can effectively modulate the compressor, because the compressor will not always be discharging at full load. The most common systems are modulation control, followed by load, no load. And we see more today a variable frequency drive on the compressor, allowing you to slow down the motor and more cost effectively deliver compressed air at part load. For larger installation, the centrifugal air compressors typically have modulation with the inlet valve modulation, so you're closing a valve on the inlet side of the air to the compressor, choking it down to approximately 70% of the compressor full output. Below the 70% point, typically you would blow off compressed air, vent it to atmosphere, and this is simply to avoid surge and destroy the engine or the compressor. So again, centrifugal machines are great. They operate oil-free, and particularly at high loads. At part loads, they are a very inefficient piece of equipment. To be able to assess the efficiency of a system in the compressor plant, in adding some of the key points what you can identify out in the plant, it will be then to have a few measuring tools on the system. And the key ones are really to have a master pressure gauge or a discharge pressure gauge, plus a temperature gauge on the compressed air as it leaves the compressor room. In addition to that, a compressed airflow measurement device, and also the power input to each of the compressors. By measuring the total CFM that you're producing at any one instant, and simultaneously adding up the kilowatt consumed by the compressors, you can easily do a calculation by CFM over brake horsepower or CFM by kilowatts. And most systems typically are in the when you're operating at about 4 CFM per brake horsepower for 100 psig system, you're operating the plant quite efficiently. You can even reach about 4 CFM per brake horsepower, but typically systems that are poorly operated with a number of compressors running in part load mode, you would see sometimes 2.5 CFM per brake horsepower. And think of it as each brake horsepower is electricity that you're buying. So if you're buying twice as much electricity to generate the same volume of compressed air, you are wasting a lot of money. And this can be quite effectively corrected by the proper control system on the compressor plant. What you see here is just a block diagram of a sample plant. This indicates 3 75 screw compressors The first unit being the top one to the top. I'll just show the indicator button here. Would be the baseload machine. So say that the plant typically is consuming something like 300 plus CFM. So this would then be the baseload machine. The second one would then be the trim machine that would allow it to come on when the load in the plant would increase. And the third one, in a good installation, would be a standby compressor, simply available in case of breakdown or some extreme condition in the facility. It's also quite helpful to have a additional discharge point in case you have major repairs and you need to bring in a mobile compressor so you can hook it up to the system. Following the three compressors, we would connect typically a wet receiver to store compressed air and also to discharge some of the raw moisture from the system. Following the wet storage receiver, filtration and the refrigerated dryer, followed by the dry storage, because now you're dealing with dry air and having a large storage volume is always beneficial to deal with variations of consumption levels in the plant. An elegant way of dealing with control of the compressed air into the plant is to have a flow pressure control device together with a control system that you might even elect to run the compressor plant at a slightly higher pressure upstream of this valve assembly. You might in some cases run the generating plant at 110, 120 psig and then drop it down to a 100 psig or whatever minimum pressure the plant would require. This is an elegant way of allowing you a very fine-tuned control of the compressed air pressure in the plant. With a device like this and the proper control system controlling all three compressors, you could manage or control the pressure on the discharge from the plant at about plus or minus 1 or 2 psig, which is an elegant way of delivering air in a cost-effective way. I wanted on this slide also to touch a bit on the economics of running a plant like this. I'm assuming typically that this plant would be running with 2 compressors. You would be consuming about 700,000 kilowatt hours per year. I'm assuming here a 5-shift operation around the clock, 5 days a week. So weekends you would shut down the plant. The electric consumption for this plant would be about, in current rates, about $70,000 per year. So typical saving, if you only look at the plant itself with the right control system, you could envision something in the order of about $15,000 savings per year, plus any savings that you can recoup in the plant. Excuse me, in line with what Herb had discussed. So first look at the load side and see if you can eliminate some of the loads, and then once you have established the load, you should be able to do some savings, particularly if the compressors do not have a how should I say, a modern or a more sophisticated control system that speak to all 4, or in this case, all 3 compressors. And as an incentive to do some of these studies, currently the Ontario Power Authority is sponsoring a program through the individual electrical distribution companies in the Saugus Enersource are assisting in the study cost is covered completely. So 100% of the study cost below a max cost of $50,000 is covered by, provided the scope is justified. I mean, that is the max amount, but the study cost is covered through that program. And also, provided that you receive the right approvals, you would also be able to capture savings of any modifications or installations up towards a number of 60 or 70% of the installation. So these are quite attractive financial incentives if you want to carry out the studies of your system with an outside consultant, as well as cost to replace components that are not operating efficiently. Just to go back to the technical aspects of this plant with 3 compressors, this picture is actually courtesy of a compressed air challenge in the US. It shows the top curve indicates the pressure monitored over a period of about half an hour, and the curve below in bolder font is the actual airflow into the plant. And many times I find compressed air pressure and flows are many times misunderstood. The plant might be complaining that at one location in the plant you don't have sufficient pressure. It's automatically assumed that this is a problem and we need to add another compressor. The issue many times is that there are too many pressure drops in the system. There are unique parts of those loads in the plant that maybe require a localized air receiver to deal with unique loads or large loads that are temporary. But it's very important to not mix up the understanding of pressure and flow, because it's a very dynamic system. By having a compressed air flow metering device outside of the compressor room, knowing what the flow is at any point, that's a great tool to analyze the system. And pressure is something you could follow on the master pressure gauge. On this case, you see a variation of roughly 3 psig. As I indicated before, if you have a flow pressure control device and a good control system that manages these 3 compressors, you should be able to bring down the pressure variation to between 1 and 2 psi, which will bring good financial return. And what you see in the system here is basically that the airflow is between 400 and 800 CFM. And a rule of thumb, again, is an efficiently operating system, 4 CFM per horsepower. So that typically indicates to me that you're dealing with about between 100 and 200 horsepower system producing these kind of flows. If you look at an individual screw compressor, there are typically 3 sort of standard control methods, and I'm looking at only one individual compressor. One technology which are used by some manufacturers is a load-unload style of control. A load-unload style of control will require substantial receivers, but receivers is basically battery of compressed air storage, so it makes good sense to have storage capacity to even out the consumption levels in the plant. And then the load-unload control would follow the straight line, indicating that in the diagram, the x-axis shows the CFM, percentage of capacity, and on the y-axis, the vertical line, percentage of power consumed. So kilowatt on the y-axis and CFM on the x-axis. And if you look at 50% of the CFM, and you go up to the solid curve, which is showing load-unload control systems, you're dealing with roughly about 60% of the full kilowatt on that compressor. If the compressor instead is an inlet valve modulation with blowdown, you're dealing with roughly about 80% of the kilowatt at 50% CFM. So you can see any part load is not very efficient or not very cost effective. You're ending up spending 80% of the full energy consumption by the compressor and only achieving about 50% of the CFM output. And with an inlet valve modulation with blowdown, at zero load or next to zero load, you're still consuming 70% of the power running that machine. So when you're coming into a compressor room and you hear the machine running, and you might be producing a very small amount of CFM output and still consuming a lot of power. That's where I think clearly you need the power meters on each individual compressor, as well as the flow meter from the whole system, so that you can determine what is the average CFM per brake horsepower, which is a great key performance indicator. The inlet valve modulation with no blowdown is slightly improved below the 40% capacity, and it approaches the load-unload style control. If we have, like many plants do have, say 3 compressors, and there's no control system communicating between the 3 individual compressors, they might be 3 different makes of compressors or 2 makes and the third one another make. So they do have only the individual control that the machine comes with. Typically compressors would then be set up in a band, in a cascading system, so that in a band of possibly say 8 psi pressure differential. So when the plant starts up, you would start up basically bringing the compressors on, and once you're up to pressure and you're discharging pressure into the plant, depending on the consumption levels of air in the plant, you would, in a cascading manner, run with 1 compressor, kick in the second compressor and the third compressor. And as compressors are controlled by the pressure discharge from each individual compressor in the cascading style, you would end up with a large band of pressure variation in the plant depending on the consumption levels. So at very low loads, you might be operating on 1 compressor but generating about 110 psi pressure. With a plant running full out with full consumption levels, you might be dropping the pressure down to 90 psi. So the pressure variation, you end up paying a lot of penalty with. And the benefit now of going to more sophisticated control systems that are linking all 3 machines together, the logic there would be then that you minimize that band to in the order of a 2 to 3 psi pressure differential. So if your plant needs 90 psi, you might set up producing, say, 100 psi in the plant with the pressure flow device, drop it down to 95 or 90, if that's acceptable, and then consume far less power and still produce the same amount of CFL. Just a few words on the cooling system side of things. If the compressors are water-cooled, methods of making the water cooling of the compressor system more efficient can include things like installing a variable frequency drive on the cooling tower fans. That way allow in the winter, or in the, I should say, in the fall and the spring, to slow down the fan, or maybe reduce the amount of electricity on the fans on the cooling towers. Other items is to look at balancing the cooling water flow so that you get the proper flow of cooling to each individual compressor and the proper cooling. You can also install systems that automatic shut-off valves so that when the compressors are not running, the water flow to that particular compressor is turned off. No idea to cool anything that's not requiring cooling. And this is just a flow chart of 3 compressors with a cooling tower and 2 pumps distributing cooling water to the individual compressors. And I won't dive into the details, but basically cooling towers is a common way of cooling compressors, especially in larger, mid-size and larger plants. As Herb indicated before, 85-90% of the energy input is lost in the form of heat, unless it's captured for other uses. And there's many methods of utilizing that heat. Because typically under adiabatic compressor conditions, the compressed air output from the compressor would be 350 to 500 F. Typically in a plant where you don't have adiabatic conditions, you would typically see maybe something like 200 or 250 degree F compressed air temperature. So you can generate by utilizing that heat in utilizing heat exchangers and heat recovery. You should be able to generate water in the order of about 120 degrees Fahrenheit to about, say, 150. On an oil-cooled systems, maximum temperature for oil-cooled systems would sit at about 180. So if you've got 120 or 150, maybe even degree water, this could be used for space heating, could provide space heating in the plant. You could use it for preheating the boiler makeup water if you have a steam system in the plant. It could be used for process heating heating process vessels, etc. And if the compressed air system is not water-cooled but air-cooled, you could set up a duct system so that you diverge or you direct the waste heat from the air cooler into the plant for space heating in the winter. And then in the summer, of course, you don't need it, so you'd have to discharge it outdoors. But the benefit of a process heating load is that typically that will be year-round, so you could use that waste heat year-round, and a cost-effective way of generating process heat. And just the last slide, I just wanted to highlight a few things that will affect the efficiency of the system in addition to what we've spoken of so far. It's also useful to have the air intake to the compressor located outside, because in the cold winter day like weather we have today, you are much more effective compressing air from a very cold temperature with more mass. The machine is going to be more efficient, and you will get more CFM per brake horsepower with an outdoor installed air intake. The other one we spoke of earlier, which is precise pressure control, minimize the pressure differential as the system operates to be in the order of 1, 2, or 3 psi. The third one is, of course, a network capacity control, where you have a control system that basically speaks to all 3 or 4 compressors and are making sure that you've got all compressors running full out, and the third one being the trim, or the last machine, if you call it, being the trim machine, and that would be the only one modulating. In particular situations where you have centrifugal air compressor, we discussed blow-off before, and that's a very wasteful thing. So running centrifugal compressors at full load and then having a trim machine that's either a screw or something that would modulate better than a centrifugal does at low load, that would be a much better design. And the VFD screw compressor. Thank you so much. That's the end of my presentation.
Well, thank you, Herb and Klaus. Now it's question and answer time. So if anyone has any questions, please type them in the chat section located to the bottom right-hand corner of your screen. Both Herb and Klaus are staying until about 2 p.m. to answer any of your questions. So a few people are typing in here. We got a thank you. Thank you to Andrea Dwight. We hope you enjoyed the presentation. So we can we have a few people typing in. Again, thank you, Alice Herrera. Thank you as well. And Darren Bourne seems to have a question here. Well, it seems that no one really has any questions. It was a really great, both thorough presentations and greatly explained. Again, if you have any questions, you can always contact Herb or Klaus. Their email information is on this slide right here, or you can always contact me here. We have 2 questions actually. So from Darren, are there uses of trans-air extruded aluminum piping good, bad? And there's 2 parts to his question, so we can maybe answer that first. Klaus and Herb.
Could you read the question again, please?
So the use of trans-air extruded aluminum piping, is that good or bad?
I'm not familiar with that. Herb, are you familiar with that?
No, I'm not either. I most commonly see the standard scheduled duct pipe.
Okay, he's added right now, there's a low friction factor pipe. Is that, no?
Yeah, I would agree with you, Herb. I mean, most of the time I've seen, basically carbon steel schedule 40 piping, typically welded. Some places you have Victaulic, but the concern would be leaks in the Victaulic couplings. But welded pipes is the most common schedule 40 I've seen.
Okay, so he said that he's used it in his plant and installed 2009 in Winnipeg, and he mentions that BM pipe has a high friction factor. I think his two of his question is the energy box from Canada Compressors used to cool oil as year-round heat for water. I'm not sure. Perhaps if he can clarify the question. Or
yeah, it makes sense to me if they're using an oil-cooled compressor and are capturing the waste heat or the heat that's generated in the oil, converting, with a heat exchanger, converting that to hot water and then providing that through space heating in the plant. So you have a hydronic heating system linked to the compressors. Makes very good sense.
I agree, and Darren, I would be very interested in your experience with these.
great, thank you so much. Oh, he says it's a new product from the US.
Okay.
So perhaps you guys can chat afterwards just to see maybe what his experience is with using this type of pipe.
Yeah, most likely, yeah. Great.
Great. Are there any other questions? Again, as I was mentioned before, both presentations were quite thorough. And that seems to be all for everyone. If you have a quick question, if you could just raise your hand, you can just click over your name, just so we can wait while you type your question. But there doesn't seem to be anything. Again, thank you again. Our next webinar is scheduled for February 16th, and that's on motor management. You can go onto our website at www.systemdesign.com